So we'll be covering pipeline reprocessing of integral field unit spectroscopy from JWST. So first, kind of a general introduction to IFUs. So integral field unit, abbreviated IFU. What does an IFU do? It's giving you both imaging and spectroscopy, such that it's giving you the image, usually kind of a small postage stamp region, little patch on the sky. It's giving you images at a range of wavelengths. So it's combining both imaging and spectroscopy. You can kind of think about it in a simplified form, looking at this cartoon illustration, kind of flowchart. On the left is, after the text, is an image of a galaxy. So it's this is illustrating the sort of small postage stamp size nature of integral field unit fields of view. So you're looking at a very small patch. And so the idea is that the IFU chops up the region into slices. So here, for this example, we have 6 slices, but it's often more. So you'll notice that the second pane in the flowchart shows the image has been chopped up into the 6 strips. And you can see the individual parts of the galaxy in the 6 strips. The next part of the flowchart, we've dispersed each of the slits by wavelength. So treating each part kind of like a slit for long slit spectroscopy. So here, like the top one is kind of the outer edge of the galaxy dispersed in wavelength, and you'll notice the middle 2 are the middle part of the galaxy dispersed in wavelength. And then finally, on the rightmost part of the flowchart, it gives you a representation of what the IFU is returning when it's doing this dispersal of the slices. Ultimately, what you get from this is a cloud of points of the intensity at a certain position in the sky as a function of wavelength. So you get what is called a cube, like a data cube, because you're getting both two dimensions of space and 1 dimension of wavelength in the data cube. So you'll get an image at every wavelength that you sample in your spectrum. And so that's kind of the middle representation on the right. You can combine different slices within the cube to produce an image, like you can combine like a small wavelength range or so forth. And also, you can think about picking a single region in the cube, or perhaps the entire cube, and then just summing up all of the signal that you get from the whole cube or some section within it, and getting a spectrum that's representative of the region of sky that over which you're summing up the emission. So like if you picked a 2 by 2 pixel here, then you'd get a spectrum representative of that 2 by 2 pixel region. I suppose I should be clear about the terminology. We use spaxel to represent an individual element within the cube. A pixel typically refers to an image, like a 2-dimensional element, an image. Spaxel, I guess, is perhaps better for a cube because it's you have data in 3 dimensions, 2 spatial and one spectral. JWST has 2 different IFUs. One is the medium resolution spectrometer on MIRI. This gives you IFU capability at mid-infrared wavelengths, so roughly speaking 5 to 28 microns. There's also the IFU on the NIRSpec instrument, and that gives IFU capability over near-infrared wavelengths, so from about as short as 0.6 microns to I think 5.3 microns is the longest wavelength that you can get IFU capability with NIRSpec. First, a bit on the MRS. So the notebook that I will be covering today was actually prepared. It's kind of continuing to be prepared. You can find the latest version of it at this GitHub link. I should also note the slides that I'm showing here and the notebooks that I'll be showing, that I'll be demonstrating over the rest of the session, all these materials will be made available along with the recordings on the Space Telescope website. And so I have here in the slides the link to the GitHub where the notebook that that I used to show today for the MRS, where the latest version of that will be. In the notebook, I will show a few things. So part of what I will show, well, kind of overall, we'll be going over the full range of the pipeline that's needed to reduce the MRS data. And it's the same parts of the pipeline for both the MRS and the NIRSpec IFU. The first is the CalWeb Detector 1 part of the pipeline. That's what we consider stage 1 of the pipeline. That's operating at individual exposure level, working to go from the raw data in which the signal from the detectors is sampled up the ramp. So we're measuring the signal as a function of time at each all of the pixels on the detector. And so the stage 1 part of the pipeline, CalWeb Detector 1, processes that to get to the point where it's fit a slope through the data, so that you have slope data, and that goes into the stage 2 part of the pipeline, CalWeb Spec 2. That's still working at the single exposure level, and the end product of that is data that's been fully calibrated, but only at the single exposure level. And then the stage 3 part of the pipeline, CalWeb Spec 3, is the part that combines all of the exposures, so that, for instance, if you have dithered data, then it's combining that, and the output products from that will be the final products. And for IFU data, that'll be a spectrum and a cube. And so the cube and the spectrum will make use of all of the exposures that. And I'll show you how to specify which exposures. So you specify them using association files. I'll show you in the notebooks how to do that. For the MRS, specifically, doing background observations is often very important for a number of reasons. One reason is sometimes the background of the object that you're looking at is fairly bright, so you need to account for that. But also, just working at mid-infrared wavelengths, you have to worry about the background coming from the telescope itself. So especially at the longer wavelengths of MRS, you have to especially worry about the background that you get that doesn't come from the astronomical target at all, or the part of sky that you're looking at. So I can go over that, and also I'll point out differences in how the extract 1D step works for point sources versus extended sources. And then I should just note that you do receive both intermediate and final products from the archive, the MAST archive. But it's often advisable to do the reprocessing. So I'll point out things that are especially important that are not necessarily the default way that you get the. They're not part of the default reductions available in MAST. So the MRS, specifically about the MRS detector, it is actually a few IFUs, four IFUs, and we call them channels 1 through 4. And the signal that comes from the 4 IFUs eventually lands onto 2 detectors. One is the MIRI IFU short detector, and the other the MIRI IFU long detector. And there's sort of cartoon representations here in the middle at the bottom. The short detector receives the signal from the shorter 2 wavelength channels, channel 1 and 2, and you'll notice that you see what look like numerous vertical strips. So these are where, if you remember the previous slide, where you're slicing up the image. So here you get the individual slices, and the wavelength direction is approximately vertical, so that the dispersion in wavelength is happening approximately vertically. And the channel 2, you can kind of see how the strips sort of curve just a little bit. But so it's this data that is later recombined as part of the data reduction, and that's how you get, for instance, the cube, is that every point on the detector is mapped to both the two spatial positions and one wavelength. And so you can build up a cloud of points and then impose a grid of spatial right ascension declination, and then also wavelength onto that to make it a regular cube. And then there are methods to do that, to take the raw cloud of three-dimensional cloud and turn it into a cube that you can output. I'll get into that a little later. How it appears on the sky. So you'll notice, so on the left pane, you'll see that the four channels have different fields of view, and they are not quite, they all overlap, at least in the part that's common to channel 1. And that the center of each is not quite the same as the other, but they all at least share the channel 1 patch, and the field of view grows larger as you go to the longer wavelength channels. So channel 1, I think, is a little over 3.5 by 3.5 arc seconds, and then 2 and 3 get larger and larger, and channel 4, I think, is just under 8 arc seconds in the two directions. So you're seeing, you have to keep that in mind. Also, so when you obtain the data, you're only obtaining it for a single grading setting, unless you've specified the multiple grading settings in your observation. So for instance, in one part of the observation, where you're reading the detector, let's say you've set the grading to the medium grading setting, then you'll get simultaneously the channel 1 medium part of the spectrum, channel 2 medium, channel 3 medium, and channel 4 medium. And so if you plot that, so if you plot the spectrum that you get from that, you'll get 4 different segments, and they're not continuous in wavelength. So in order to get a full 5 to 28 micron spectrum, and it's not quite, it's more like 4.9 to 27.9 microns, but to get a full continuous spectrum, you need to obtain, you need to include in your observation all 3 of the grading settings, short, medium, and long. So that means that there are 12 segments to a full MRS spectrum, 3 grading settings for each of the 4 channels. So 12, and I call them bands. So like one of the 12 segments would be a band. Like the channel 1 medium grading setting would give you the band 1B, for instance. And the way we do the notebook to reduce the MRS data is we can specify, and we do, specify which detector to reduce the data for, and also the grading setting. And so here, for this example that I'll be going through in a little bit, we're looking at short wavelength detector, that's MIRI IFU short, and the medium grading setting. So the data will be bands 1B and 2B that you'll eventually see the spectrum for. Okay, so a bit about backgrounds. The background emission, especially in channels 3 and 4, can be very important. So dedicated background observations that's why we motivate them as much as we do. In addition to removing the astronomical background signal and any telescope signal, they're also useful for removing some detector artifacts, such as warm and hot pixel, variations from warm and hot pixels, and coherent striping. There are 3 different ways to subtract the background that the pipeline allows for. One is I guess you'd call it a pairwise subtraction that can happen in the stage 2 part of the pipeline. That's the part of the pipeline we call JWST 2. And I can point out when we get to it in the notebook where you do that. So you can specify subtracting individual background exposures from science exposures. I should note that it's advised, if you're going to do this, it's advised to have high signal to noise dedicated background observations to do that, and that they be of equal depth to the science observations. Another way to subtract background is in the master background part of the stage 3 part of the pipeline, JWST 3. This does model-based background subtraction. It calculates an average background across the entire field of view at every wavelength, and then subtracts the background that way. Lastly, there's also background subtraction that can happen in the extract 1D step in JWST 3. So if you are extracting the spectrum of a point source, then it's basically doing aperture photometry at each of the slices. So you have an aperture where you're summing up the signal, but then it computes a background annulus around that and does the equivalent of background subtraction from aperture photometry as part of the going through the slices in extract 1D. For extended sources, the entire field of view of the detector is used as the extraction region, and there is no annular background subtraction. But you have to keep in mind that the extraction size increases with each channel because the field of view of the channels 1, 2, 3, and 4 increases as you're going to longer wavelengths. For point sources, so there's aperture, it's basically doing aperture photometry. Keep in mind that there are small errors in WCS between bands, and this can cause the location of the extraction to be off. And so there's a keyword in extract 1D, IFU _autosend, that can center on the point source in the cube before extraction to try to account for that. Let's see. Also, and then there's a keyword for cube build where you set output type to band to get individual cubes from cube build. Okay, an important thing for the MRS is fringing. So the instrument itself gives rise to fringes that show up in the data that are not intrinsic to the astronomical signal from the source, and it's just they arise because of the way that the instrument was built. And so there are ways to account for those. One of the ways is there's a step in JWST 2 that divides by a fringe flat. And so in that case, the fringe flat would take into account fringes that come from a uniformly illuminated aperture. So, I mean, that doesn't necessarily happen often, that your source would be extended and be uniformly illuminated, but if it did, then that step would take care of those fringes. But that, that's typically not the case. Point sources and extended sources where the emission is varying over the field, the fringe flat step won't take care of that, so there is another step that does residual fringe correction. And there are two ways that that is done. One is at the two-dimensional level, where I don't know if I have it here. I think I can show it later. Where the fringes show up in the two-dimensional slope data, and so there's a step, the residual fringe correction step goes through and um, removes the fringes at the two-dimensional level. If after doing all of that, you still have fringes in the spectrum that you get from Extract 1D, there's also a one-dimensional residual fringe correction algorithm that can be used as well. Okay, so that was a bunch on the MRS. For the NIRSpec IFU, I just have a few slides. Here's kind of a cartoon representation of the MSA mask. That's the mask where the light enters for the different modes of NIRSpec. So you can see the four quadrants for the for doing MOS observations, the four MSA quadrants. In the middle, the sort of middle strip here is where you see the aperture in red for the IFU on NIRSpec, and then there are also the slits for the fixed slits modes of NIRSpec. And here on the left is kind of an inset zooming in an actual picture of the NIRSpec IFU aperture. You can see the magnetic arm that can close and obscure the aperture if requested. So NIRSpec has two different detectors, NRS1 and NRS2, and for certain of the observations, both of the detectors are required. Like for NIRSpec IFU observations, if you're using the high resolution gratings, then it needs to disperse the light over both of the detectors. So that's illustrated here, where one of the higher resolution gratings are required or have been requested, and this would be an IFU observation of a uniformly illuminated source. So you can see there are 30 slices here from the NIRSpec IFU, and they're arranged so that the wavelength is dispersed roughly horizontally in this case. So you're dividing the NIRSpec IFU aperture up by 30 in each direction, and the field of view is 3 arcseconds square, so that means that each pixel in the field is about 0.1 arcsecond on a side. NIRSpec has 3 different spectral resolving powers. There's the one that we give it sort of a rough value of 100, but really it varies from about 50 at shorter wavelengths up to, I think it's 200 or 300, close to 5 microns wavelength. But that's the prism disperser, and that gives you the full 0.6 to 5.3 micron spectrum, all in one. And then there are also the medium and high resolutions spectral resolving power gratings on NIRSpec, and so those come in different segments according to the different filters that are available. A couple of caveats with NIRSpec. So actually both MIRI and NIRSpec, and for that matter, I think the other near-infrared instruments on James Webb, suffer from the effects of cosmic rays. When it comes to NIRSpec, we refer to the effects that we see on the detectors as snowballs, sort of big balls of the effects of the cosmic ray. I'll show them the effect in one of the NIRSpec notebooks. And so there have been algorithms developed as part of the pipeline, and specifically in the stage 1 part of the pipeline, CalWeb Detector 1, that help correct for these snowballs. And so I can get into that. And also another thing important to remember for NIRSpec is the outlier detection step. Sometimes in certain versions of the pipeline, this step can be a bit too aggressive, so it can be a good idea to turn it off. And I can point that out in the notebook.